let's get right into the paper. Today we are breaking down If You Want Coherence, Orchestrate a Team of Rivals, Multi-Agent Models of Organizational Intelligence by Vijay Raghavan and the team at Isotopes AI.
Quite a mouthful.
It is. Here's the 1-minute summary. So the core problem is that single large language models, they act like solo workers. You have these huge blind spots, they're terrible at verifying their own work, and when they hallucinate, there's no safety net.
Not at all.
The solution this paper proposes is a shift from an AI person to an entire AI office. We're talking about an architecture with over 50 specialized agents. Think planners, executors, and critics.
And the key mechanism isn't consensus, it's not a vote.
No, it's veto authority. You have specialized critics who did not write the code checking the output against criteria that were declared up front. If a critic says no, the internal team just retries, and the user never even sees the error.
So what were the results?
They tested it on 522 financial reconciliation sessions, the multi-agent system, 92.1% success rate. The single-agent baseline was just 60%.
But there's a trade-off. There's always a trade-off.
A big one. It costs about 40% more in compute credits and adds a lot of latency. But for high-stakes domains, this reliability, it might be the only viable path forward.
That's the headline for sure. And for the engineers listening, this paper really challenges this whole race for a single God model. It argues that reliability comes from structure, from having opposing incentives, not just from having a bigger parameter count.
Okay, welcome to AI Paper Podcast. We are going deep on this one because I think a lot of us are feeling the fatigue of the one prompt to rule them all strategy.
Oh, absolutely.
We've all been there, right? You craft this massive perfect system prompt, you give it to GPT-4 or Claude, and it works like 80% of the time. But that last 20%, it's a nightmare.
It's a complete nightmare. And the industry has been obsessed with this idea of the AI person, this one brilliant analyst who can do everything, reasoning, coding, you name it. But, think about how that works in a real company. If you hire a brilliant analyst and give them zero oversight and they make a mistake, who catches it?
Nobody. Not until a client is screaming at you anyway.
Right. If that analyst hallucinates a number or just messes up a simple logic chain, there are no guardrails. This paper is basically arguing we need to stop building better individuals and start building a better AI office.
You need an org chart.
You need an org chart. You need specialized roles. And crucially, you need what they call organizational intelligence.
Organizational intelligence. Okay, that sounds a little bit like corporate buzzword bingo. What does that actually mean in terms of architecture?
It means that the reliability of your output isn't a property of the model itself. It's a property of the system you design around it. It actually relies on friction. You want a planner pushing for a really comprehensive plan, an executor who's just trying to get things done, and then a critic whose entire job is to just say no.
That sounds incredibly inefficient. We usually try to remove friction from our pipelines to lower latency and cost. Why would I deliberately introduce a critic who just blocks things?
Because the alternative is silent failure. In these high-stakes environments, and this paper specifically looks at financial reconciliation speed is way less important than accuracy.
Good point.
If you process an invoice in 2 seconds, but you get the dollar amount wrong, you haven't solved the problem. You've just created a liability faster.
Fair enough.
No.
Okay. Before we get into the specific agents, the planner, executor, and critic, the paper does a really good job of just laying out the current landscape of multi-agent systems. They break it down into 3 types. I found this super helpful because multi-agent has kind of become a catch-all term lately.
It really has. So the first architecture they describe is tool chaining. This is the most common pattern you see today. You have an agent, reasons a bit, it calls a tool like a calculator or a search API, it gets a result, and then it decides the next step.
So it's all sequential. Step A leads to step B leads to step C.
Exactly. And the fatal flaw there is compounding errors. If step A is just a little bit off, say the agent retrieves the wrong document, well, step B just assumes that document is correct and keeps on going.
The error propagates down the chain.
Right. And usually the agent that's checking the work is the same agent that did the work. It's grading its own homework.
Which works about as well for AI as it does for high school students. Okay, so that's tool chaining. The second one they mention is sub-agent parallelization. This feels more like the fan-out pattern.
Right. Think of a manager delegating tasks to 10 interns all at the same time. You check the database, you check the web, you write the summary. It's fantastic for throughput. You can do a ton of work at once.
But I'm sensing a catch.
The catch is that they're all blind to each other. The paper gives this great example. Imagine one subagent assumes the fiscal year ends in December. and another assumes it ends in March.
Uh-oh.
They both come back with perfectly valid answers based on their own private assumptions. When the parent agent tries to aggregate them, you get a hallucination born of that conflict. The parent has no idea that there was a mismatch in the first place.
So you just end up with this Frankenstein report at the end. Which brings us to the third architecture, the organizational council, which is what this paper is all about.
This is their team of rivals approach. It's all about stage-gated oversight. Work flows from a producer to a critic. And this is the critical part. The user only ever sees approved work. They use what they call the Swiss cheese model of defense.
I want to dig into that, but first let's look at this org chart. If I'm building this system, who am I hiring? You mentioned planners, executors, and critics. Let's start with the planner. Is this just the agent that breaks down the prompt?
It does that, but it does something much more sophisticated first. The planner in this system defines the acceptance criteria right up front.
Acceptance criteria, you mean like unit tests?
Exactly like unit tests. It's basically test-driven development for agents. The planner doesn't just say, go analyze this invoice. It constructs a schema. It says the final output must be a JSON object. It has to contain a date field in ISO format, a vendor name that's a string, and a total amount that's a float.
But hang on, if the planner is also an LLM, couldn't it just hallucinate bad criteria? Or, set the bar too low so the executor passes easily?
That's a risk, but it's a different kind of reasoning task. Defining the shape of a correct answer is actually easier and less prone to hallucination than doing the messy extraction work itself. Plus, this is where you might use a stronger, more expensive model like GPT-4 or Opus just for that planning phase to make sure those criteria are rock solid.
Okay, so the planner sets the rules of the game. Now, the paper mentions a step here that I think gets overlooked in a lot of these autonomous agent discussions.
Yeah.
The user gate.
Yes, this is huge. The planner generates a plan and the acceptance criteria, but it doesn't just start, spending your money on execution. It pauses. It presents the plan to the human user.
So I, as the user, I actually have to sign off on the plan.
You check the strategy. You say, yes, this plan makes sense. Or you spot an issue, maybe the planner missed one of your specific requirements, and you can correct it right there. This human in the loop at the planning stage prevents the whole system from going down a rabbit hole for 20 minutes based on a bad premise.
That feels like it solves the whole runaway agent problem. So human approves the plan. Now we get the executors and writers, the hands, they write the code, and then the critics.
The critics are, I think, the most interesting part of this whole architecture. In most ensemble methods, we see voting, right? You run 3 agents, and if 2 say A and 1 says B, you just pick A.
Democracy.
Right. But this system is not a democracy. It's a bureaucracy with veto power. If the code critic looks at the executor's work and says, this syntax is invalid, or you ignored the acceptance criteria about the date format, the whole process just stops.
Really?
It doesn't matter if the planner and the executor are high-fiving each other. If the critic says no, it is a no.
And what happens then? Does it just crash? Does it ask the user for help?
It does neither. It enters an internal retry loop. This is the organizational intelligence in action. The executor and the writer, they see the critic's feedback. Hey, you missed the invoice number.
Yeah.
And they try to fix it. They rewrite the code, they run it again, they submit it to the critic again.
And the user sees none of this is happening.
The user is off grabbing a coffee. They have no idea that these agents are basically arguing in the background. They only see the final result once the critic finally signs off on it.
That distinction, the internal loop versus a user loop, that seems absolutely critical.
Yeah.
You mentioned the Swiss cheese model earlier. How does that apply to the critics?
So the Swiss cheese model is a risk management concept. The idea is that every layer of defense has holes, flaws.
Okay.
But if you stack enough layers of cheese, the holes shouldn't all line up.
Okay.
In this system, they use different types of critics. They had a code critic looking for syntax errors and API misuse. And then they had a chart critic that was looking at visualizations to see if they actually matched the user's intent.
And I'm guessing these critics found different things.
Almost zero overlap. The paper highlighted that the errors caught by the code critic were completely different from the ones caught by the chart critic. If you just had one general manager agent reviewing everything, it probably would have missed half of these issues because its attention would be split. By specializing, you close more of the holes in the cheese.
Let's talk about the technical implementation for a second. There's a section in the paper about something called context ray tracing. Now, honestly, when I first read that, I thought they were trying to apply graphics rendering to text, which made no sense to me. What are they actually talking about?
It's a fancy term, but it's for a really disciplined approach to data hygiene. The core problem they're solving is context contamination. If you're doing financial analysis, you might have a 50-page PDF or a massive CSV file.
And the standard approach is to just stuff that whole thing into the context window, right? You argue it or you just paste it in.
Exactly, but stuffing it in is super dangerous. First, it's expensive. Second, and this is more important, it confuses the model. If the model sees some stray number in a CSV row from 2021, it might hallucinate that as the answer for 2023. Context ray tracing is about strict information hiding.
How strict are we talking?
Think of it like a clean room in a laboratory. You have the scientists, the reasoning LLMs outside the room, and you have the dangerous samples, the raw data inside the room. The scientists never go inside. They just write instructions, which is code, and send those instructions into the room.
So the LLM never actually sees the raw invoice.
It never puts the raw text of the invoice into its reasoning context window. It writes Python code that executes on a remote kernel. That's the clean room. That code opens the file, extracts the specific data point that was requested, and sends back only that result.
Ah, I get it. So the LLM receives something clean, like total $500, instead of receiving the entire chaotic document.
Precisely. It keeps the brain focused on logic and reasoning, not on parsing unstructured garbage. The ray tracing metaphor comes from this idea that you're only illuminating the specific pixels or data points you need, rather than trying to render the whole scene at once.
That makes a ton of sense. It also sounds like it would help with privacy, too. Yeah. If the LLM is running on OpenAI's servers, but the code execution is happening on my local secure server, the LLM doesn't technically read my private data, right? It just directs the extraction.
Correct. All the PII stays in your execution environment. The reasoning model just sees the metadata or the sanitized outputs.
I want to ground this in the case study they ran, because financial reconciliation sounds really dry, but anyone who's had to do it knows it's a total nightmare. What exactly were they testing?
They took a stack of 9 PDF invoices, healthcare bills, telecom receipts, cloud hosting invoices, and they tried to reconcile them against a QuickBooks expense report.
And anyone who's ever dealt with a healthcare invoice knows they are basically designed to be unreadable.
They're a complete mess. Tables spanning multiple pages, hidden fees, dates in totally weird places. The paper details this one specific failure mode with a healthcare invoice. The single agent system tried to parse it. It looked at the document, couldn't find a clear invoice number label, and it either hallucinated one or just returned a null value and moved on.
Because the single agent just wants to complete the task. It wants to give an answer.
Exactly. It wants to please the user. But in the AI office, the planner had set that schema. Invoice number is required. The executor tried to grab it and failed. The code critic saw that failure and used its veto. Unsatisfactory, missing field.
So it just kicked it back to the team.
4 times. The internal team looped 4 separate times. They tried different extraction logic. They tried different regex patterns. Finally, on the 4th try, the executor wrote a script that correctly located the number. The critic approved it, and only then did the process move forward.
4 retries. I mean, if that was a human doing it manually, that's just persistence. But for an AI, that is the difference between a working product and a demo toy that looks good once.
That is the team of rivals effect. The friction forced the system to work harder and get it right.
But, and there is always a but, all of this friction, all these retries, that costs money.
Right.
We can't ignore the economics here.
And the economics are the painful part. They compared this system against a single agent. That single agent had about a 60% accuracy rate.
Which is basically a coin flip plus a little bit of luck. You can't use that in production for finance.
No way.
Yeah.
But the team of rivals hit 92.1%. However, it used 38.6% more tokens. And the latency, well, the single agent took maybe a minute or 2. The multi-agent session took nearly 13 minutes.
13 minutes. I mean, for a background job, that's probably fine. But I can't have a user sitting there waiting 13 minutes for a response.
Exactly. This is not for chatbots. This is for asynchronous back-office automation. But they broke down the costs even further and found something really important about what they call the heavy tail.
This is the level 3 recovery concept, right?
Yes. They found that most invoices were actually easy. They cleared in 1 or 2 loops, cheap and fast. But a small percentage, about 28% of the sessions, were these level 3 difficulties. They required 6 or more retries.
Oh, wow.
These few hard cases accounted for 68% of the total recovery costs.
So you're spending almost all of your compute budget on the hardest 25% of the work.
Which mimics human organizations perfectly. The routine work is cheap. It's always the edge cases that cost you time and money and headaches.
Even with all this, though, the 50 agents, the critics, the 13 minutes. They didn't hit 100%. They hit 92.1%. So what happened to that other 7.9%?
This is what they call the glass ceiling of automation. The paper calls it residual error. And these weren't coding errors. These were failures of ambiguity.
Ambiguity.
Yeah, situations where the user's intent wasn't clear, or the invoice was so garbled that even a human probably couldn't read it, or it involved a domain rule that just wasn't in the prompt. For example, is this team lunch expensible? That's not a math problem. That's a company culture problem. The AI can't know that.
So the paper is suggesting that there's a hard limit to how much we can automate without keeping a human in the loop for those final tricky edge cases.
Exactly. The goal shouldn't be 100% automation. It should be the reliable identification of the 8% that needs a human. If your system can confidently say, I handled these 92 perfectly, but these 8 are really weird, please check them, that is a massive win. The problem with single agents is they try to do 100% and just lie about the 40% they failed on.
That's a great distinction. Reliable failure is almost as important as reliable success. So, zooming out, what's the big takeaway for the ML engineers listening to this? Do I need to go spin up a Kubernetes cluster with 50 agents tomorrow?
You don't need 50 agents tomorrow, but you do need to stop writing monolithic prompts. You need to start thinking about org chart engineering. Decompose your task. Who is doing the work? Who is checking the work?
And they don't have to be the same model, right?
No, and they probably shouldn't be. This architecture lets you be composable. Use a fast, cheaper model like Llama 3 or Haiku for the writer or executor roles. They're great at generating boilerplate code. But for the planner and the critic, the roles that require that deep reasoning and scrutiny swap in your frontier models, use Opus, use GTC4.
That makes a lot of sense.
Yeah.
You don't pay a senior principal engineer to write the CSS for a login button, but you definitely want them reviewing the architecture.
Precisely. You allocate your intelligence budget where it actually matters. And because the agents are modular, if a better writer model comes out next week, you just swap that one agent out. You don't have to retest your entire system from scratch.
It feels like the era of prompt engineering is really evolving into system engineering.
It is, and it raises a kind of a philosophical question. We've spent years trying to make AI helpful and agreeable. We train them to be nice. But this paper proves that to get to the truth, you might need agents that are willing to be disagreeable. You need agents that argue.
A room full of arguing experts.
It's not always pleasant, but it's effective. That intersection where the planner, the executor, and the critic finally stop fighting and actually agree, that's the only place where you can really trust the output.
Well, I think we can all agree that reliability is definitely worth the argument. This has been a fascinating look at Team of Rivals. If you are building agentic workflows, I'd highly recommend reading the full paper to see the breakdown of their DAG structures.
Definitely. It feels like a blueprint for the next year of AI development.
Thanks for tuning in to AI Paper Podcasts. We'll catch you on the next deep dive. Go build some friction into your systems.